Okay, so for section 1.5, we're going to be learning what a derivative is. Introduction to derivatives. So the derivative of a function, y equals f of x, is a new function that we will call y equals f prime of x. So we can let's write that out. So we can either say this as f prime, that little exponent of 1 is prime, f prime of x, or you could say it as the derivative of f of x. So the derivative, and we'll explain what that is in a second. The derivative of f of x or f at x. You can say either, right? From grade 11, f of x or f at x. All right. So, and the derivative of f of x, the new function, f prime of x, is going to represent the slope of a tangent line. So the slope of a tangent line, or the instantaneous rate of change, which we've looked at before, we know is at one point in time. So if it's at one point in time, we're using the tangent line because the tangent line only crosses a graph at one point. At any point on the graph, y equals f of x. So the derivative function is defined by the first principles definition for the derivative if the limit exists. So the limit has to exist. So let's say here the limit as h approaches 0. This is just the simplified version of this one. So this, if you remember, equation is our difference quotient. Our difference quotient from before. F prime of x now is equal to the limit as I approach of f of x plus h minus f of x divided by all over x plus h minus x. But if you remember, if I have x minus x, they cancel out. So this is just the formula that we will use. It's the simplified version. F of x plus h minus f of x over h. And we're going to take the limit of that as h approaches 0 to get my derivative. So let's say that these here, the blue line, the green line, and the pink line, if you see our graph here, let's call it f of x. We've been using f of x, but again, we can say g of x, s of x, any letter, right? These are my secant lines, the blue, the green, and the pink, because a secant line crosses the graph twice, right? 1, 2, you can see the little red dots there, 1, 2 along the green. The black line is my tangent line because it's only crossing the graph once. And these are my secant lines. So just to go over an example, if you remember from before, what we did was, excuse me, what we did was choose a point right beside my tangent point. If I wasn't able to get the instantaneous rate of change, I needed to use the average rate of change. And so I chose a point right beside it. But for example, in a graph that looks like this function f of x, I have a point here on the blue line, the blue secant line, and a point here. This distance is not very accurate then, right? I'm a bit of a distance away. So let's say the distance between these 2 points is not the best estimate of the tangent line. So if I wanted to find the instantaneous rate of change, that point here is too far away. It's not going to be very accurate. So basically what we're saying is, let's get rid of the secant lines and use the tangent line to find the instantaneous rate of change. And that's what the derivative is doing. So the derivative is finding that instantaneous rate of change along the tangent line. So what are some different notations, different ways that we can just indicate that we're finding a derivative or write the derivative of a function? So y equals f of x is my original function if I wanted to get the derivative of it. So to find the instantaneous rate of change, it would be f prime of x, like I have up here. Or I can also write y prime, because again, f of x is on the left-hand side of an equation that represents y usually. So it's kind of saying the derivative of y, or dy over dx, which you'll see more so in university. Or again, this is like dy over dx, but instead of the y, right, y is equal to f of x. So instead of y, I'm writing it out as f of x. That f of x is basically with the d as the numerator, but just not to have the d and the f beside each other. It's just written a little bit separate so it's easier to see. D of f of x over d of x. So we would probably use f prime of x and y prime more often, but you will see this one also. If the derivative does not exist at a point on the curve, so if this point, the derivative does not exist, then the function is non-differentiable at that x value, at that exact value. That means I can't find the derivative. And this can occur when these two cases occur. So if the function is discontinuous, which we just learned about, right? If it has removable discontinuity, or if there's a jump discontinuity, or remember the infinite with the asymptote discontinuity on the graph, then at that point where those discontinuities are occurring, then it's non-differentiable. Then that means I can't get my derivative. So if it's discontinuous, then it's not differentiable. Or in this case here, this is new. The function has an abrupt change. So here it says a corner at P. So I'm decreasing on my line, and then all of a sudden there's a sharp, let's say even 90-degree turn, and then I'm increasing. Or I have a curve and I'm decreasing, and then all of a sudden I change and I start to increase, and that would be called a cusp at P, a cusp and a corner. So in these two cases, at this point, let's change our color on this. At this point here, and at this point here, the derivatives do not exist. It doesn't mean they can't exist anywhere else along the line or along the curve. I'm just talking about like at that corner and at that cusp where there's an abrupt change, the derivatives will not exist. So these are continuous functions, right? However, the graph is non-differentiable just at these points, even though they are a continuous function. So there's an example of a continuous function and a point on the continuous function where it's non-differentiable, and then also if it's discontinuous, okay? Let's jump into an example. For the function, so f of x, also y, you could think of it as, equals negative 6x squared. Use the first principles to differentiate. So what I'm going to be doing here is finding the slope of the tangent line. So differentiate means I'm finding the slope of the tangent line, or I'm finding the instantaneous rate of change, basically both, right? Finding the slope of the tangent line or the instantaneous rate of change. So the first principles means I'm going to use the difference quotient technique. Using the difference quotient. So what I'm going to be getting in my answer, but we'll go over that again afterwards, is I'll be getting an equation as my answer that represents the instantaneous rate of change at different x values, so that if I plug different x values in, I can figure out what the instantaneous rate of change is at that x value using that new equation that I have, which would be the derivative equation. So in order to find that, I need to write out my difference quotient, right? The one with the star from up above. So f prime of x, I think I'm writing this too big, I'm gonna run out of room already, equals the limit as h approaches 0. You do need some room for this. I'm going to find f of x plus h, right, minus f of x, and then the simplified one where it's just over h. So we have our equation here, f of x equals negative 6x squared. So instead of x, I'm going to substitute in x plus h. And then here I don't need to substitute because x is the same x. I can just use this equation to subtract and then over h. So I only need to do a little bit of work here for the first part. Now that work I'll just put off to the side over here You can put it off to the side, to the left or the right, depending on where you started writing this. So I'll put it over here. I have some room. So I need to figure out what f of x plus h is. So what I'm going to do is I go back up to the formula, the right-hand side. So I have my negative sign and I have my 6. And then instead of x, I put a bracket and I replace it with x plus h. And then I go back up and I finish the rest of the equation, which is just the squared. So negative 6x plus h squared, but then I have to simplify that, right? So I have negative 6 and I can do x plus h, and I can do FOIL. So then I would have negative 6. Again, x times x is x squared. X times h is plus xh. They're both positive. Plus another xh. It's just easier than writing hx, right? It doesn't matter the order when you multiply, but here if you write it the same way, you're more likely to catch that these are like terms. Plus my last times last, h squared. And then I can multiply the negative 6 in, but maybe I should clean this up first. So x squared, we have the plus 1 xh plus 1 xh, so plus 2 xh plus, just make sure that they're all positive right now. And then bring in the negative 6 distributive property. So negative 6x squared, negative 12xh, negative 6h squared. Negative 6x squared minus 12xh minus 6h squared. That's hard to say. So right now I'm just going to show you off to the side. This is my simplified equation, which I can highlight. And I have over here written down as h approaches 0, as my limit approaches 0. So if I replace my h's with 0, I'm just putting this off to the side. You can look at it, you can write it down for the first time. I'm just explaining what we're doing to explain the thought process for the next step over here on the left, but I won't be doing this and you won't have to do this every time. So I'm just saying if I were to replace my h's with 0, I would have negative 6x squared minus 12 times x times 0 minus 6 times 0 squared. And then to finish off the rest of the equation, right? This is just f of x plus h. If I was in a minus, that function at negative 6x squared will end up turning into a positive 6x squared. And then to finish off the equation, I have h as the denominator, but the h is now 0. So what would that end up being? So I have 0 times x, which is 0, times negative 12, which is 0. 0 squared times negative 6 is 0. So I end up, and then I have negative 6x squared plus 6x squared. Hold on a second here. So that's 0. So the point is that I have 0 over 0, which is, if you remember, an indeterminate. So that is where we're going with this one. This will always happen in these questions. So we will need, remember, indeterminate means, oh, there's more work to do. I need to further factor or further simplify or further rationalize, which is what we're doing anyways. We're going to be going further here. So this is a step that you'll automatically always do. I'm just saying this is why we're doing it, is because we're getting an indeterminate, which means we have to go farther before we can plug in our 0 in for h, before we can put our h is equal to 0. So that's not until further along, because we have to simplify further first, because if we do it now, that's what happens. So again, you can just remember that. You don't have to write down necessarily this portion. I'm just showing you where we're headed and why we're not putting h equal to 0 right away, so we can skip this step. All right, so let's go back over here. Let's change to black and continue on here. So we have equal to the limit as h approaches 0 of f. Oh, I don't need f, sorry. Let's erase, not f. We have f of x plus h is this equation here. So we're going to write that out. Negative 6x squared minus 12xh. I'm finding it's hard to even look at where exactly it is. So definitely that box around it helps so I don't accidentally write down the wrong line, and I double check it too. And then finish it off, right? Minus f of x. F of x is the equation negative 6x squared, which we already said will change to a positive, over h, which we'll do in the next step. We keep writing the limit as h approaches 0 until I put in my zeros in for h. So until I do that, I keep writing the limit down. So negative 6x squared minus 12xh minus 6h squared plus is the only difference there from the minus and the minus multiplied by each other over h. And hopefully something's looking a little bit easier here, something that, remember, we're simplifying indeterminate. We have to go further here with something. So then we would have, oh, negative 6x squared and positive 6x squared. And I think that's as far as we can go. So that's fine. That's simplified a little bit. So now we have the limit as h approaches 0 of negative 12xh minus 6h squared divided by h. And what we want to do is we want to get rid of the h on the denominator. Since h, right, cannot equal 0, is there a way we can get rid of the h of the denominator and then not have to worry about it? And because there's an h in every term up above, which should always happen, you can factor out again. You can factor out here, for example, a negative 6 and an h. But remember what we said even in the previous videos is you don't even have to go that far as factoring out the constant. Just all we want to do is get rid of the h on the bottom. So just factor out the h. So if I factor out the h, I need to write limit again because I haven't subbed in h is 0 for my h's. And I'm going to factor out the h, and then I'm left with negative 12x and negative 6 with 1h divided by h. And then just like we wanted to, we have these h's canceling out. And I'm running out of room, so I'm just going to go up here. But again, hopefully, if you have more room than me, just continue on. So that equals the limit as h approaches 0 of what's left over. I can leave it in brackets, negative 12x minus 6h. So guess what? Now we've gone as far as we can go, right? Now we're going to sub in h equal to 0. So then now that I'm subbing it in, I don't need to write the limit or as h approaches anymore. I can just go ahead and write out negative 12x minus 6 times 0. That's just 0. So I'm left with negative 12x. So that means that my derivative, therefore, what was I trying to find? The derivative of f of x. So f prime of x, therefore f prime of x is equal to all that work, and at least it's simple, is an equation of negative 12x. So again, I'll be getting an equation that represents the instantaneous rate of change at different x values. So why don't we move this up so we can talk about that further. So I will just recopy this equation down since I need to clear this screen and move this up. Okay, so let's write that down again. So we had here, sorry, oops, need my pen. Therefore, f primed of x is equal to negative 12x. That is my equation, my derivative equation. So determine the following and then interpret the results. So there is a little prime there, a little 1 there, be careful. So what it's saying is I need to figure out what f prime at 1 is. So I use my equation. If f primed at x is equal to negative 12x, then I'm looking for f prime at 1. I'm just subbing 1 in for x, and I get an answer of negative 12. So let me finish the 3 first, and then I can explain using all 3. What am I doing here? What am I finding here? What does that mean? So f prime at 0 is equal to negative 12 times 0, which is just going to be 0. And f prime at -2 is equal to -12 times -2, which ends up being, be careful that you write +24. So here are my answers. X equals -12, X equals 0, and X equals 24. You don't have to circle them, it's just for me to highlight them. So what are these values? So you might think, well, if f of x, right, was to equal -12, then that would be a y value. These are not y values. These are derivative values. So we need to represent the slope. They represent the slope of a tangent line at various x values. So at this x value of 1, we have the slope of the tangent line at the x value of 1 is -12. So the easiest way to show that would be, if I go back to my equation, y equals -6x squared. So just hopefully, I've never switched screens doing a video before, and I'm hoping that this will work. Okay. Too bad that I have to erase the work that I did though to go back. So hopefully you have that down and we can just come back to it. Unfortunately, I have to clear it right now. But if we go back to y equals -6x squared, which is this graph here. So you can use any graphing, you can use Desmos if you want. Then if I look at the one that I just did, f prime of 1 equals -12 for I there. So the x value is 1. So at an x value of 1, right, my y value is, it would be -6, right? So it would be -6, but my answer was -12. So what that means is if I were to draw, it's talking about the slope of a tangent line. So if I was to draw a line there, which I'm not going to do that good of a job, but I will try at -6. So if I was to draw, and it's trying to just cross that parabola once, right? So let's say that this was the line here. You get the idea though, right? Probably should be moved over to the left a little bit more slanted. And then crossing, that's the tangent line, crossing once only at -6 there. And you can see that it's a negative slope. And you can see that the graph is decreasing at that point. So if I was to figure out the slope of that line, which you know how to do that from grade 9, right? The slope of that line would be -12. That's what we're saying. So another value is f at 0 that we figured out, the second one, I there. The x value of 0, to move back up here. Come on. The f value of 0, I'm not increasing and I'm not decreasing, right? I'm at a turning point there. So how would I draw a tangent line at that point? So we've gone over that before. The tangent line at that point would just be simply a horizontal line, right? So what's the slope of a horizontal line? So the slope of a horizontal line is 0. So see how my answer there of f prime of 0 was equal to 0? So the slope of the tangent line at x equals 0 is equal to 0. Hopefully that's starting to make sense now. Let's look at the third one just to really drive it home. So we have f prime at -2, and we had an answer of 24. So my x value is -2. So here's -2 here. If I zoom out, if I'm at -2 here, I'm going to zoom out even more. Probably one more. So at -2, if I was to plug -2 into the original equation, -6x squared, right? -2 squared is 4, so 4 times -6 is -24. So I have -2 and -24. You can see right at that value there. So let's put even a dot there, just so we know what we're talking about. -2 and -24. So there's my tangent point. So there's my x value and there's my y value. But my answer is 24. So what that means is at -2, and it's positive. So at -2, the slope of the tangent line, so again, if I were to try to draw a line and the graph is increasing at this point, right? So if I was to draw the tangent line, the slope of this tangent line would be 24, is what we're saying. So if I was to draw a line that cuts through and intersects the graph at just one point, at the point where x equals -2, the slope of that line would be 24. So that's what we're finding out. Okay, so if we go back, there we go. So that's what these answers were that I was talking about. Okay, so they are not y values, just to go over that again. They are derivative values. So at that x value, it represents the slope of the tangent line when I'm going through that x value, that tangent point, let's say. Okay, let's look at determining an equation. Determine the equation of the tangent line at x equals -2. So I want an equation of a tangent line. So the equation of a line, right, from grade 9 is y equals mx plus b. And what information do I have so far? So I know that if I go up here, this answer, which was here, I'll write it in again, and then I'll just erase it again. This answer here, f prime at -2, right, was -12 times -2. We had an answer of 24. So I already have x value at -2 here, which is the same x value of -2 here. And I had an answer of 24, which we already said was the answer to the slope of the tangent line. So I already have my slope. If I erase just this part, there we go. So I already have my slope of the tangent line. So because this is the slope of the tangent line, we want to write it out as m with a little capital subscript t, x plus b. So I know my slope of the tangent line is equal to 24. I know my x value is equal to -2 because it told me. So I have b and y to figure out. Well, I can't figure out two unknowns. There must be one that I can solve for. I have my original equation, right? My original equation is y equals -6x squared. So if I know that x is -2, if I just put in -2, then I have -6 times 4, and then I have -24. So I know that my y, so just to highlight, I know that my y is -24. My slope of the tangent line is 24, and my x value is -2. So that's okay. If I only have the b to solve for, that's what I'll do to solve for b. So plug in what I know. So I have -24 in for y. My slope of the tangent is 24, and just be careful, multiplied by x of -2 plus b. And then I would just stop and make sure that those are in properly, that the y is on the left-hand side, your slope was positive, and my x value I put in properly. So -24 equals, multiply those together, -48 plus b. How do I get b by itself? Take that -48, right, and bring it over to the other side and add. So -24 plus 48, the -24 stays negative, right? So my answer is +24. So there's a lot of 24s in this question. That's just kind of coincidental, just the way it was. So I want to determine the equation of the tangent line. So therefore, the equation of the tangent line, the equation of the line at x equals -2 is y equals, and again, we only want to fill in our m and our b. So our m was 24, or slope 24x plus 24, and they just both happen to be positive. Okay,